Okay, in this lecture, we are going to study how to draw the Nyquist plot and find the range of K for stability. I mean the range of gain for stability. Here the question is GH equals K divided by S plus 1 into S plus 2 into S plus 3. You are asked to draw the Nyquist plot and find the stability for different values of K. Now we need to first find the expression for magnitude and angle. To find the expression for magnitude, we take K divided by root of omega squared plus 1 into root of omega squared plus 4 into root of omega squared plus 9. Now if we substitute omega equals 0 in the expression for magnitude, we get it as K by 6, because this is root of 1 into root of 4 into root of 9, which will give you 6 in the denominator. So this will become K by 6. Now to find the expression for angle, for the numerator the angle is 0, and for the denominator 0 minus tan inverse omega minus tan inverse omega by 2 minus tan inverse omega by 3. Now you have got the expressions for magnitude and angle. Now we draw the plot, the Nyquist plot. So this is the initial part of the Nyquist plot, the first part of the Nyquist plot, and we take the mirror image. So this is the mirror image, right? This is the initial part. This is the initial part, and we take the mirror image. So it will be like this. Now for extra encirclements, we check the number of poles at origin. We don't have any pole at origin here, so there are no extra encirclements. So by this point it terminates. At point A it terminates, and it's starting at point A also. It starts from point A and it terminates at point A. Now we need to find the number of encirclements around -1 plus j0 to comment on stability. But here the number of encirclements around -1 plus j0 depends on the value of K, because the point at which it goes through, it intersects the -180-degree axis, this point. If this magnitude is greater than -1, the magnitude of -1 plus j0, then that means -1 plus j0 is inside this, right? Or this can be at -1 plus j0, that is a second case, or this can be less than the magnitude of -1 plus j0. So to find that, we need to find the magnitude at this point, find the magnitude at the intersection point of -180-degree axis. So first we need to if the angle is -180-degree, we have the expression for angle here. So at angle -180-degree, you need to find the omega, and if the corresponding omega is substituted in the expression for magnitude, we'll get the magnitude at this point, right? So that is what we are going to do. Now the point at which the plot crosses -180-degree is phi equals -180-degree. So this is the expression for phi. Angle GH equals -180-degree. If you substitute, then omega is the only unknown. If you find omega from this point, and if you find omega from this point, you'll get it as omega equals 3.33 radians per second. Put this omega in the expression for magnitude of GH to get the magnitude at point B here, to get the magnitude at point B. So you are getting it as K by 60. Right, now this magnitude, it can have three cases. This magnitude is greater than 1, that means magnitude of -1 plus j0, or equal to the magnitude of -1 plus j0, or less than the magnitude of -1 plus j0. So we are taking three conditions. The case 1 is magnitude of K by 60 greater than 1. That means the point -1 plus j0 is inside. That is a first case. So when magnitude of K by 60 is greater than 1, that means K is greater than 60. If K is greater than 60, we'll apply the Nyquist criterion, where n equals p plus minus z plus. We have two encirclements here. This is 1 and this is 2. Okay, so if we draw a line like this, it intersects at two different points. So two encirclements are there. So n is equal to -2, then p plus is 0. There are no right half open loop poles in the given expression, so p plus is 0. So z is equal to 2. We are getting z as 2. So that means it's an unstable system. That means for K greater than 60, the system is unstable. Now in the second case, magnitude of K by 60 equal to 1. That means it is at the point B itself. -1 plus j0 is the point B itself. That is the second case. For that case, mode of K by 60 equals 1. That is K equals 60. The number of encirclements is 0. No encirclements around -1 plus j0 here. So n equals 0. P is 0. P plus is 0. So z plus is equal to 0, which means it's a stable system. no RHP, closed loop RHP poles, which is Z plus. Okay, so it's a stable system. So for mode k by 60 equals 1, it is a stable system. Now for case 3, we are taking minus 1 plus j0 outside this loop here, outside this loop. That means our condition is mode k by 60 less than 1. That means k less than 60, n equals 0. Again, no encirclements because the point is outside. Then p plus equals 0 from the given open loop expression. Then z plus equals 0. So it's a stable system. Because this is z plus equals 0 implies closed loop transfer function poles at RHP is 0, and that means it's a stable system. Now the range of k for stability. So for case 2 and case 3, the system is stable. That means for k less than 60 and k equal to 60, the system is stable. That means for k less than or equal to 60, the system is stable. Right. Now, what is the lower limit for k? This we don't know. Right. To find the lower bound, we'll see the condition. How to find the lower bound? Whenever the stability condition is less than a certain value, then lower limit is decided by the intersection point of the plot with 0, and that particular point, that particular magnitude is taken as if it is taken as greater than -1, then we will get the lower bound. That means here the intersection point of 0 is here, right? Intersection point of 0 is here, right, at this point. So at this point, omega equals 0. At omega equals 0, magnitude is k by 6. Magnitude is k by 6. Then magnitude is k by 6. So k by 6 greater than -1. We are taking it as k by 6 greater than -1. That means k greater than -6. So the lower limit is -6. So you substitute it here, -6 less than k less than or equal to 60. That is the condition for stability for the range of k for the condition for stability. Thank you.